Here's Einstein predicting gravitational waves, laying the foundation for a laser, and 100 years later, his gravitational waves are found with lasers.
Yes. Einstein was kind of smart. From the time I first started working on gravitational waves until we succeeded was 50 years. Some things take a long time. We do build on each other, and none of them by themselves are smart enough. This Nobel Prize really belongs to 1,000 people.
If I can see farther than others, it's because I've stood on the shoulders of giants who have come before me.
And that's the nature of science. It's very promising, but it's going to continue on into the next generation before the ultimate success is had, very, very, very probably.
This is StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And today, we're featuring one of our one-on-one conversations, this time with Professor of Theoretical Physics, Kip Thorne. Kip Thorne, welcome to StarTalk.
A pleasure to be with you, Neil.
Oh my gosh, we are coming from your home office in Pasadena, California.
It's a wonderful office. My son designed this part of the house and built it, and my brother designed and built all the furniture.
These are really useful people to have in the family.
It's a wonderful family to be in. They're the practical ones.
I've actually known you for some time, not that we were beer drinking buddies, but
I think we've drunk beers together in the Canary Islands.
Yes, we did. Okay. I stand corrected. But my first exposure to you was you were one of the three authors of this book called Gravitation. And we used to joke, of course, it was the only book where you learned about it just by carrying it around.
and I think we probably wrote it before you were born.
Possibly. Although I'm older than you might think. This book is a graduate level treatise on basically Einstein's general theory of relativity. At the time I acquired the paperback of it, which this is, it's tough making a paperback this thick, but this has the exact proportions of what was then the Manhattan Yellow Pages. So we used to call it the phone book.
Yes.
Just affectionately, may I add. It was brilliantly conceived because I don't know if you can notice on camera, there are tabs are different colors, as white and black, and they represent two different paths through the book. One is sort of the elementary path, and one the more advanced path, except it all looked advanced to me at the time. So whose idea was this to come up with this book?
Coming up with the book, I think it was sort of grew out of discussions that Charlie Misner, John Wheeler, my PhD advisor, and I had a few years after I got my PhD.
Those are the three co-authors there.
Those are the three co-authors. Mm-hmm. And so it sort of grew organically in the...
That's the best kind of projects to have.
1960s and early 1970s.
Mm-hmm, mm-hmm. Yes, I was born before the 60s.
Oh, really?
So on here is Charlie Misner, who was at the University of Maryland.
Yes.
And so my copy of this, I had you sign it, and then I spent a year teaching at the University of Maryland. So I quickly went over to his office and had him sign it. But before then, I started out in graduate school at the University of Texas, where John Archibald Wheeler they stole him from Princeton, I think is what that, or lured him from Princeton, I think.
Yeah, that's an accurate statement.
And so I had all three of them sign it. In fact, John Wheeler's course that he taught in general relativity is where I met my wife.
Wow.
Yeah, she has a PhD in mathematical physics. So we met in relativity class. Just thought I'd say that.
Very romantic place to meet, Very romantic.
Very romantic. And John Wheeler used to give out a penny if you caught an error that he committed on the front board. So I have one of his pennies. I don't remember. It was not a big thing. It was like, it was a typo or something, or whatever, the written version of a typo. But anyhow, it's just a delight to meet again with you. And what prompted this was you have a lot of accolades, of course, including the Nobel Prize. Okay. But more importantly than that, you were science advisor on the film Interstellar.
Well, I was more than science advisor.
Yes, you were. You were executive producer.
I was more than executive producer. It grew out of a treatment that Linda Opes, an ex-girlfriend of mine.
Oh,
and I
Linda Opes,
wrote.
a big producer of sci-fi films.
Yeah, she a big producer of films of a wide variety. But Linda and I dated in 1979, 80, and she was too high-strung for me, and I was too nerdy for her. But we became close friends.
Wow.
And
well, who knows this? Why didn't I know this? Stop. Why didn't? Where would one learn this? We need a physicist gossip column. Is that right?
Yeah. It was some years later after Carl Sagan, who set us up on a blind date, by the way. That's how we met.
Okay.
Some years later, Linda called me up and said, "Would you like to brainstorm with me for a movie?"
Wow.
And we did, and that's how Interstellar was born.
So was that at the time?
It really was the creation of the Nolan brothers, because they took what we had given them, which was basically a structure and a venue for the movie, The Warped Side of the Universe. And they ran with it and changed our story almost completely and made it into a great film. But all the seeds came out of Linda and me.
It's at the time, I mean, you're a professor at Caltech, the Richard Feynman professor at Caltech, now emeritus. Caltech is a pretty high-level place. How was it viewed for you to say, guys, hold on, I'm going to make a movie now? What is that? How does that received by your colleagues?
I think they were all enthusiastic. Good. Caltech is a different kind of a place than some other more stuffy universities.
Oh, okay. Okay. I never hung out much at Caltech, so I couldn't judge the mood or the tone.
Yeah, no, look, we're on the edge of Hollywood. The Hollywood folks come over and, Big Bang Theory was based on Caltech.
Right, they didn't call it Caltech. What did they call it?
They did call it Caltech in the first few episodes.
Okay.
And then they stopped using the Caltech name because the shirts, that's Hollywood speak for the attorneys.
Oh, yeah, the stiff shirts, yes, up in the office.
The shirts got scared that they might do something on screen that the Caltech shirts wouldn't like, and the Caltech shirts might sue the Hollywood shirts. And so they stopped using Caltech name.
And in the film, which I adored, what was it called? Real Genius?
Yeah.
Real Genius. They were at Pacific Tech, all right? That was where all the smart kids were. So, of course, Pasadena is in, I can't say foothills of Hollywood, but you have a proximal awareness of this huge industry.
Yeah.
And you know that science fiction matters as a genre.
Well, and some of us love it.
I love it. I'm sign up every time. And so Interstellar, I think it introduced many people to authentic gravitational physics for the very first time.
Well, Interstellar was unlike almost any other film. I think there were precursors in 2001 and in Contact.
Yeah, Carl Sagan's Contact.
Carl Sagan's Contact. And the point is that science, lots of science was baked into that film from the very beginning because of the way it was born and because of the close collaboration I had with the Nolan brothers and built in right from the very beginning. And baked in, and a science that in which the guideline that we worked from is that nothing in the movie would violate well-established physical laws, and all the wild things would at least spring from science in some manner.
As any good science fiction story should be, but there's not enough.
Well, there's nothing wrong with fantasy films, the Harry Potter style, for example. It's just a different genre.
By the way, that film, you you must have known. You said, okay, we're going to have to help people out. Give a guy a break, okay? They're trying to see the movie. They're trying to follow what's going on. What the hell's happening? Why did the guy get old? Why is he younger than his mother? What's going on? And you upped and said, let's help a person out.
Yeah, well, I would put it a little differently. Okay. I saw it as a superb opportunity to use this film as a motivator to get people interested or intrigued in science. And then there would be a bridge to the science through this book.
Admit it, you created a gateway film.
It was a gateway film, yes.
So The Science of Interstellar, New York Times bestseller, Kip Thorne, with a foreword written by, of course, Christopher Nolan. And it says, spoiler alert, this book explains the fantastic climax and ending of Interstellar.
And so let me tell you how this issue came about. Chris said to me early on, I would like to make a film where the ending is as mysterious as the ending of 2001, A Space Odyssey.
That's a high bar.
That's a high bar, but he greatly admires Stanley Kubrick and that film. And so somewhat later on, as we were talking about the ending, and we had lots of conversations about the ending, he said, well, you can explain the ending in this book that you're planning to write.
So he volunteered you to write the book.
Well, no, I was already planning to write the book, but he identified that as the place where the ending will get explained. He was not going to explain the ending. He would leave it mysterious.
Not in his film. He was pulling a Kubrick on us.
That's right.
In fact, we interviewed Christopher Nolan. If you're an archive diver, we've got a whole episode with Christopher Nolan, even before Interstellar was produced. And as we know, so many of his movies, he plays with time in some kind of interesting way. If I remember correctly, he talks about how influential 2001 A Space Odyssey was to him back in 1968. That would have been.
Yes.
So let me ask you just a couple of things about the storyline. And I have an issue with it, if I may. But I don't know if I ever went public on this, but I figure I'm in front of the man himself. So if I have an issue, it would be here and now.
You're gonna get turned into a journalist who's challenging me.
No.
Gonna give me a tough time.
Yeah, I can't. This can't be just all okay. Softball. Let's play a little hardball. So I guess my issue, we're looking for a planet. Again, this is in the themes of the movie. We're looking for a planet like Earth, similar enough to Earth that we can send people there to continue our civilization and our species. Is that a fair characterization of a plot line, of the plot line? Okay. And it turns out there's like a wormhole that can make that happen a little faster, because otherwise you don't live long enough to travel the distances with the rockets available to hit those destinations. Okay. I'm just thinking, this blight on the crops that was starving everyone on Earth, requiring that we jump ship, literally jump ship, to go find another ship, another spaceship planet. It seems to me that whatever effort it takes to find another Earth, travel through a wormhole, terraform it, ship 1 billion people there, whatever that effort is, seems to me to be a bigger effort than just telling the biologists, come up with a serum that could fix the crops. Even today, we have full knowledge of crop genomes. Just fix it. Whatever it is, just go in there, nip, tuck the DNA, fix it. Isn't that cheaper, easier, faster than wormholing your way off this planet? That's where I'm coming from.
So you think that all problems can be solved by humans with human technology on a time scale? You have such faith in humans. Come on.
So I'm the optimist here. Okay,
so let me describe. This characterizes how this movie was done. So when it was Jonah Nolan, Chris's brother, who came up with the idea that he wanted a blight or something like that. And so we said, okay, we will bring together the best biologists we can, who are experts on these kinds of things, put together mostly Caltech biologists, and we had a dinner, and we brought out very expensive wine for them to drink, and we set up a recording.
In vino veritas, in truth there is wine.
Yes.
In wine there is truth, yes.
And so we had a conversation that lasted about three or 4 hours at the Caltech Faculty Club, the Athenaeum, about what would be the best backstory here. There are two types of blights. There are generalized blights that attack lots of crops. And there
Lots
are
of different species of crops.
Lots of different species of crops. But they are generally fairly benign blights. And then there are blights that are very specific to a particular crop, and they can be very lethal blights that may totally wipe out that species on Earth even. But basically for Earth and life on Earth to survive, you better not have a vicious generalized blight. But according to the biologists that I discussed this with, they didn't know of anything that would prevent the development of a very vicious generalized blight. So that's what occurs in this movie. And it's something that biologists have never seen, but they cannot rule it out.
Okay, so let me repeat what I think you said. They have vicious, lethal blights that attack a species, less lethal, generalized blights that cross species boundaries, and they can't rule out a lethal blight that would cross species.
That's right.
And so that's what's happening in this film.
What's happening in the film. And, and that's what the biologists
all right, I'll give you
Earth
that.
in the back. So there's a back.
I'll give you that. Okay.
Okay. So anyway, this film is full of backstories because of the way we did it. It's as I say again, it's unlike almost any other film, and that these issues were like that. Were vetted by the world's best experts.
Right.
In the process of the writing of the screenplay.
Okay.
As we're diving into Kip Thorne's impressive work, one thing is clear. His theories have reshaped our understanding of the universe. So you might think the latest Nobel Prize for Physics would go to someone like Thorne, but it went to computer scientists instead. Their contributions to machine learning is undeniable, but still a surprise for the world of physics. Some reports focus on the godfather of AI regretting his invention, while others don't exactly see the problem. In moments like this, access to diverse perspectives is critical, making ground news essential. They're a platform created by a former NASA engineer who saw a bigger problem down here on Earth than up in space, and the way we consume information and how heavily that shapes our worldviews. Ground News responsibly uses technology to add clarity to a world full of opposing opinions by showing perspectives from around the world, how reliable are sources, and blind spots, so you can see important stories barely receiving attention. Here's why that matters. Critical thinking drives the pursuit of understanding complex concepts. It challenges established beliefs, and it's the only way we can make new discoveries. So for those of us who are curious enough to dive into new perspectives, now is the perfect time to give Ground News a try. Take advantage of their massive 50% discount on their top-tier Vantage plan and get access to every feature we've shown and more for only a limited time. Use our link at ground.news/StarTalk or scan the QR code to subscribe. As we continue exploring Kip Thorne's groundbreaking series, remember, Ground News can bring that same level of critical thinking to how you stay informed. Now, back to the show.
Well, I got another one. Okay, you're one for one. All right. When they're on the black hole planet, okay, and then they see this wave coming.
Okay, it's Miller's planet.
Miller's planet,
that's
sorry.
the water planet.
The planet orbiting Gargantuan.
Mm-hmm.
Gargantua,
yeah.
Okay? The strength of tidal forces are highly sensitive to the distance you are to that which is causing the tides. Highly sensitive, okay? But every illustration I've drawn or taught about tides, they're not so peaky. They're much broader in their representation on a planet. And so there they are, wading in water, but then they see this single wave come. And if it is a single wave, as we've seen with tsunamis, it actually takes water away from what's ahead of it. Because it can't just be water out of nowhere. It's drawing water from its vicinity. So my two issues was, if it's tidal, would it be that peaky? And if it's any kind of wave, how could it still leave the water laying around its vicinity and then just be that big as it came by?
So there is a type of wave called a solitary wave on water that was...
Oh, you could tell me you brought wave people together and had that lunch. Is that what you could tell me?
No, this particular kind of wave was discovered in the 1700s by, I've forgotten who, a physicist in England who saw a boat that was being pulled by horses, and it was just starting up, and it created this wave that traveled down a channel, a canal, and it was peaked like the wave in Interstellar. Though the wave in Interstellar, I have to admit, it was exaggerated. There was
I don't mind exaggeration.
There was some exaggeration in the peak, but it traveled down the channel. It never broke. Most waves in the ocean, they break.
Okay, just so we can get the picture, because we're talking about centuries ago. When you say a channel, that would be a channel or a canal.
A canal.
And then there's a towpath on the side.
A towpath.
And then people, and more likely beasts of burden, would drag things through the canal. Because canals themselves don't typically have current.
Drag a barge down the canal.
A barge, exactly.
Yep. And so this barge was dragged down the canal, and it was just starting up, and it created this wave that...
on the startup.
On the startup, and it just headed out and just took off and went down the channel. And this guy got on his horse and he followed down the channel, and it went down the channel. You gotta love
curious physicists. Nothing gets by.
And it went down the channel for I don't know, a mile or two, without changing its shape, without
breaking.
And so the theory of these waves is that there are two different effects that cause a wave to steepen or disperse, and the two can balance each other out in a stable sort of a way.
And give it longer life.
And give it a long life. And so aside from the issue of friction, if there were no friction, it would just live forever and keep propagating in a very stable way. There's a mathematics behind it, something called the Korteweg-de Vries equation that this is a solution of. But anyway, these waves then...
So that equation, I presume, has both kinds of waves in equilibrium somehow represented
the two
as a
effects,
static wave.
The dispersion and the steepening. The steepening is due to nonlinearities. The dispersion is due to the fact that the higher wave... the higher parts of the water travel faster than the lower parts of the water.
I didn't know.
If you're at the ocean, you see a little tiny wave, it travels quite slowly. You see a big wave, it travels quite fast.
And that's why the crest of the wave will actually break before the rest of the wave gets there.
That's right.
Is that part of the reason?
That's right. Unless that's being balanced out by dispersion, which is... Anyway,
I love it. No, it's good. Good. Anyway, no, I'm loving it.
I'm getting this slightly confused, but anyway, the two effects balance each other and to produce this very stable solitary wave. And so in the movie, for this stable solitary wave, the height of the wave is, and I've forgotten the number, but it's something like 6 times higher than the depth of the water.
Got it.
So there's a problem now in the movie because they're walking around in shallow water and this wave is high, and so it's got to be deep water.
Okay,
but they're on an island. This is the backstory. Again, there's always a backstory.
So they're on a subterranean, a subsurface island.
Yeah, you got to read it in my book.
Okay,
they're on an island, and this wave diffracts around the island. They hardly notice the island at all. So again, it's all explainable, except there is a bit of exaggeration. The CGI wave was made somewhat more peaked, somewhat
and we'll
higher
give you
than it
that.
would
We'll
be.
give you that. It's a movie and it's Hollywood. Yeah. But what you're saying is this wave might have been caused by some effect other than the tidal forces of the black hole.
Yeah. Well, this wave is caused, in fact, by the fact that this time is much slowed on this on this planet. So the planet has been put into the orbit around Gargantuan not that long ago, as seen on the planet. Though it's a long, long time ago, as seen from far away, and it is it's like Mercury, like the moon keeps one face toward Earth, or Mercury keeps one face toward the sun due to tidal effects. This planet is distorted by tidal effects, and it's swinging back and forth. It has not yet settled down to one face toward the planet, and that swinging back and forth is generating this wave.
Okay,
that's all in the book.
He weaseled out of another one. Okay.
There's an enormous amount of science in that book.
I must have missed that when I went through the book. And one last point.
You didn't study it carefully enough, Neil.
One last point. We took our show to Oxford recently, and I interviewed at Oxford, I think it was a postdoc, and his name is Andrew Mummery. Postdoc, and he showed us a recent paper he published. I don't know if you've seen it recently, like within the past 18 months. And he's a theoretical physicist, and he alerted me, something I'd never knew. I love the field, but it's not my active professional field, that in the vicinity of a black hole, there is an innermost orbit, because of course you can orbit any source of gravity, even if it's a black hole. But for black holes in particular, there's an orbit within which the orbit is no longer stable, and it will spiral into the black hole itself. And according to his calculation, to get the time dilation necessary in the scene with the black hole planet, which was huge. Remember, they were on the planet for like 15 minutes or whatever. How long?
Well, 1 hour on the planet is 7 years up at high altitude.
7 years up in their spaceship, okay?
Spaceship,
and the guy who they left there, he's like gray and unshaven and everything. And we're like, oh my gosh, there's some serious Einsteinian physics going on here. His calculation showed that for that difference, for that extreme difference in time dilation, requires that planet orbit so close to the black hole that would be on an in the unstable zone. And so I just thought I'd tell you that.
My calculation says otherwise. So,
and where's his Nobel Prize? The other guys.
the formula is in the book.
In this book.
Yeah.
So we don't have to go to your graduate textbook for that.
No. Well, not for the answer.
Okay.
If you want to derive the formula, that's a lot of work. So let me tell you the story behind this.
So everything's got a story. Okay.
So Christopher Nolan says to me one day, he says, I want the hero and Cooper, the hero in this movie, to go down onto this planet.
Cooper, played by Matthew McConaughey.
Yeah, that's right. Professor Brand's daughter is played by Jessica Chastain. Christopher Nolan says to me, he says, I want in this movie that 1 hour on Miller's planet is 7 years up at very high orbit or back on Earth.
He prescribed that.
Yes. And I said to him, that's impossible because the planet will fall into the black hole. He said, go do a real calculation. I've already learned that your off-the-cuff reactions can be wrong, and I should not trust you unless you do a real calculation.
There's a good Hollywood producer. Go back and give me the answer I'm looking for.
Well, and so I went back home, and I did a real calculation, and I was amazed that the last stable circular orbit, which is what we're talking about, is if the black planet spins fast enough, the last circular stable orbit can have as high a redshift, as high a time difference as you might wish. But that requires
the dilation.
It requires that this black hole spin extremely close to the maximum possible spin. And so in the book, I give the formula for what is the spin of the black hole that is required to produce a given amount of slowing of time.
I did not know that.
And so it's an approximate formula, but it's a formula that can be derived, though it takes a fair bit of algebra.
Okay, so the one would just learn about would probably be the lowest stable orbit around a non-rotating black hole.
That's right,
and that's a clean.
That's a clean problem, and that's what I was thinking when Chris said I want this. And I knew that if I made the black hole spin, that it would get closer, but I couldn't imagine. I could not imagine that nature would provide it a orbit for a black hole that spins fast enough that it could provide this much of a slowing of time. But it does. It does. At least, unless I made a mathematical error. But I don't think that's likely because I used Mathematica.
Okay, you had tools to help you do this.
To check my calculation.
Because it's not just an analytic solution.
Well, it is an analytic solution.
But it's very complicated.
But it's very complicated. Yeah.
Okay.
Well, it's a power series solution.
In the end, I think our hero character is inside the black hole. We come to understand this. And he has access to a timeline that wouldn't otherwise be available to him. And he sees his daughter's bookshelf.
Well, he's no longer inside the black hole.
Where is he when he's doing this?
So this is the key thing that's not explicit, that you only understand if you read my book. You didn't read it well enough.
Okay. Busted. No, I read a lot of it. Let me say, I read some of the biology.
And it was a long time ago, too.
Yes, okay.
So he when he gets inside the black hole, he is scooped up by a spacecraft that was built by this advanced civilization that provided the wormhole to him and to humanity. And it's called the Tesseract. And Tesseract is a 4-dimensional cube, 4 spatial dimensions.
And that's why in there you saw, I guess, the past and future all kind of simultaneously.
All related to the Tesseract.
It felt very higher dimensional.
Yeah, so that's right. So
he succeeded there.
This Tesseract, so let me back up. I'll tell you a story. So early on when we were working on the film, Christopher Nolan said to me, he wanted to take his hero back to Earth, Cooper back to Earth, by a different route than the wormhole, 10 billion light years away from the Earth. How's he going to do it if it doesn't go through a wormhole? He said, well, I want to take him back faster than the speed of light. And of course, I say to Chris, you can't do that. It violates the laws of physics. He says, go do a real calculation. I said, I don't have to do a real calculation. And so we discussed this for a week, and then he threw in the towel. He said, okay, I believe you. And so what do we do? And so I said, well, you put him, he goes inside the black hole. He gets deposited on the 3-dimensional surface of a 4-dimensional sphere. And this 4-dimensional sphere is a spacecraft that can go into the bulk, into the higher dimension. And it goes out of the black hole, not through the horizon. It can't do that. It goes up
through the 4th dimension.
And up through the 4th space dimension, or what's called the 5th dimension in the movie.
Sure.
His time is the 4th dimension, and goes back to Earth. And the distance back to the Earth is less than the distance between the Earth and the sun. Even though it's 10 billion light years inside of our universe, up in the bulk, it's a very short distance. And so he can get back very quickly.
This is the higher dimensional space-time in which we are now having this.
So he gets back very quickly, riding on the surface of this 4-dimensional sphere. He said, I like it all entirely, except I'm going to use a 4-dimensional cube instead of a 4-dimensional sphere. That's a tesseract.
Yes.
And so that's what happens. And when you see Cooper out there sort of flailing around at the beginning of the Tesseract scene, he's being carried by the Tesseract back to Earth, but you don't know that's what's happening until you read my book. By agreement between Chris and me. That's the only way anyone's ever going to know. So anyway, he's carried back to Earth, and then everything is happening when the Tesseract is docked in the higher dimension beside his...
giving access to his life in that past time.
That's right. So it's docked in his home in his daughter's bedroom.
Okay, so now he's pushing books off the shelves that land on the floor, and through some clever cryptographic judgment, he's spelling out words with the first letter of the title of each book. Okay, here's my issue. I had no problems with Tesseract, black hole, 4th dimension, 5 dimensions. How does he know the title of each book from the other side of the book?
So I don't remember that's how he's actually...
He's pushing books out.
No, I know he's pushing. He's pushing
books out from this side.
Yeah.
And all he sees is the other side of the library shelves.
I guess I had forgotten that he was spelling things out based on the first word.
Oh, you forgot.
I forgot, or I didn't know, or you're wrong.
So that was one of my. I just had an issue there.
That one I don't know.
Oh, okay.
I don't know.
Okay, so you're 3 for 4 on this.
Yeah, he probably has a photographic memory.
A perfect memory of the other side of the book.
Yeah,
okay.
yeah.
What's this I hear that you can use a wormhole to travel backwards in time? Does the math check out? Does the Einsteinian physics check out? And does that mean I will just show up a younger version of myself and shake my own hand? Is that what you mean by that? Or do I no longer exist in the time that I left for my younger version of myself to see that? And didn't Hawking put forth a time travel prevention conjecture or something? What's going on there?
So this is all an outgrowth of my phone conversation with Carl Sagan when he was working on the novel For Contact, where he triggered me to start thinking about wormholes. And then having started to think about wormholes, it became pretty obvious to me rather quickly that if I give my wife, Carol Lee, one mouth of a wormhole, and she carries it at high speed in a rocket ship out into space and then back, and I keep the other mouth at home. If she sees me age by 50 years back on Earth, well, she ages only 1 year going out and coming back. But if we look through the wormhole at each other, we see each other aging at the same rate. Just imagine we hold hands and we look at each other's wristwatches. It's ticking away at the same rate. So through the wormhole, we've aged at the same rate. We're the same age. But looking outside the wormhole,
through a normal universe,
she's aged 1 year and I've aged 50 years. Something weird has happened. The wormhole has become a time machine. If I just go over and go into her wormhole mouth, and come out, I'll meet my younger self.
Okay, now Hawking said, no, we're not going to allow this. There's some conjecture yet to be discovered that'll tell you can't do that.
Well, so the story, we get there. You're going too fast.
I'm going too fast. Sorry.
So then I talked to friends at the University of Chicago. Physics, it's crucial to talk to friends. They tell you where you're all at. They tell you when you made a mistake. They straighten you out. And they pointed out to me that it might be that when the time machine is turned on, it'll self-destruct, basically, they said. And I said, I don't understand. They said, go do a calculation. So I went and did a calculation. And the issue is, and they had guessed, and basically, that's oversimplified, but Bob Garroch and Robert Wald at Chicago. Anyway, it turns out that at the moment that you can first time travel, the first thing that goes through, it can be vacuum fluctuations of light, say, that enter her mouth of the wormhole, come out of my mouth and go back and arrive back at her mouth at the very moment they started out. Now you have twice as much at the same place in space and time.
So this is a runaway.
So it's a runaway. And so you now have twice as much, and then it goes around again. Now you have 4 times as much, goes around again. So this runaway builds up.
Just like the feedback between a microphone and a speaker.
Precisely.
And it just runs away.
It just runs away. And it runs away. And this runaway shows up in the quantum mechanical calculation that I did.
You're bumming me out, dude.
Together with Sung-Won Kim, a Korean postdoc of mine.
Okay, I'm going to be a movie director and say, Kip, go home and figure out how to do this. Pull another rabbit out of the hat here.
Well, anyway, we discovered this. Stephen, I think, and one of his, Stephen Hawking, And a student of his, I think, had more or less the same discovery at the same time, except Stephen probably just did it all in his head because that's the way Stephen is. Anyway, so then Stephen and I started corresponding about it by email and talking on the phone about it and so forth. It appeared to me, looking at the details of the calculation, that in fact the explosion, if I designed the time machine just right, the details of the explosion would not be strong enough to destroy the wormhole. And Stephen then showed me that I was wrong, and we argued back and forth for a while. And finally, we came to agree that the explosion becomes strong enough that quantum gravity enters in and then holds the answer tightly in its grip. And so we won't know whether the time machine self-destructs until we understand the laws of quantum gravity.
So let me be fun and obscure here.
But then we come to the Hawking's cosmic censorship conjecture.
That's what it's called.
Yeah. The conjecture that, in fact, in the end, the laws of quantum gravity won't save the day. The wormhole will be destroyed, and any time machine that any advanced civilization makes will be destroyed when they try to turn it on by these vacuum fluctuations. And thereby, as Hawking says, keeping the universe safe for historians of all species.
It reminds me of the ultraviolet catastrophe, where you run the calculation, this is going to blow up. How does this even work?
Yeah.
And then out comes the discovery of the quantum, which saves the day, right? And this could be a calculation waiting for another branch of physics to open, or another progress in the known branches of physics to resolve.
The LIGO team has perfected a technique called quantum precision measurement, which is based on manipulating vacuum fluctuations in order to circumvent the uncertainty principle. And so this business of manipulating vacuum fluctuations is something we do in modern physics.
If memory serves, Carl Sagan came up to you and said, for contact, I want to go far distances quickly. How am I going to do it? Can you cook up a wormhole for me?
Carl phoned me back in the 80s.
When he's writing the novel, because obviously the novel predated the movie.
That's right. And he said that he wanted, that he'd already written the book, the novel. It was already in page proofs. And he said, I've got this novel, it's in page proof. The publisher's not going to be happy if I change it, but I really need some help to see what the truth is, and then we'll figure out how to deal with this. And he said that I have my heroine traveling through a black hole to get to the star Vega. And I said, that's rather dangerous. There's a singularity in there.
Okay.
There's a singularity in there, and you can't get through, get to the star Vega. So what you actually need is a wormhole. But there is an issue that wormholes implode. They collapse so quick that nothing can get through. But I'll see if I can figure out how to hold a wormhole open just for you, Carl. And so I was going with
it's like Rent a Physicist, right? It's like whatever your needs are.
So I was getting in a car that morning to ride with my former wife to our daughter's graduation up at Santa Cruz. And so Linda said, I'll drive and you calculate. So she drove and I calculated and I fiddled around, and then it became fairly obvious. Turns out some other physicists figured this out sooner, but that's the usual thing with me. I figure it out, and then I go see, did people know this before or not? So anyway, I figured out that if you had what I like to call exotic matter that repels gravitationally, and you put it inside the throat of a wormhole, that can hold the wormhole open.
It'd be like pushing it outward.
Yeah, that's right. It basically repels the walls of the wormhole to hold them open. And it turns out that will do it. But you have to have enough exotic matter to hold the wormhole open. And I deduced a formula for how much you had to have. And it basically says the following. If you move through the wormhole...
Let the record show he's about to describe how to make a wormhole.
No, only how to hold it only how much exotic matter you have to hold it open.
That sounds like a recipe to me, but go on.
So you travel through the wormhole as close to the speed of light as you possibly can. Just very close to the speed of light. And you add up all the energy density all the way through the wormhole of stuff that's in the wormhole. The net has to be negative, and then you can hold the wormhole open. So it basically means you've got more negative energy than positive energy.
And because we have nothing known as exotic matter.
Oh, yes, we do.
What?
Yeah. And so
is this in your basement? What do you mean? What do you mean? Oh, yes, we do. What is our exotic matter that would fulfill this purpose?
So if you
should we turn off the camera now? Is the government going to show up in your driveway? Okay, go.
Well,
Men in Black.
I learned about this from Yakov Borisovich Zeldovich in Moscow.
Zeldovich
was one of the inventors of the Russian hydrogen bomb.
Okay.
And I learned this from him.
All right.
Okay. He was really brilliant. I learned about vacuum fluctuations and how important they can be, and how powerful it can be if you can manipulate them. And so if you take a box and you remove everything that can possibly be removed from the box, you're left in the end with tiny fluctuations of everything that possibly could have been in the box. So electric fields, you have fluctuating electric fields, fluctuating magnetic fields, fluctuating protons, electrons, fluctuating deGrasse Tysons.
So this creates a form of pressure inside the box?
Well, so there's vanishing pressure and not vanishing energy due to renormalization. Now that's a nasty word in physics, but you can measure energy by whether it produces gravity or not. And although these fluctuations that are there, you can think of them as particles, say particles of light, flashing in and out of existence randomly.
So why isn't this not the virtual particles that people speak of?
So it's virtual particles.
It is that. Okay, we've spoken about those on our show before.
Okay, so you have virtual
with Brian
particles.
Greene, in fact.
So you have virtual particles in the vacuum.
Popping in and out of existence.
Popping in and out, and you can't stop it. You can't prevent it. However, you can take fluctuations from one region and borrow them and put them in another adjacent region for a little while. Or if you put an electrically conducting sheet, say a sheet of superconducting metal here, then that will suppress the fluctuating electric fields parallel to the metal, because they would create an infinite current flowing in that metal, and that would wipe out the electric field parallel to the metal. And so
is that an element of the Casimir effect?
Yes, that's the Casimir effect.
It is, yeah, where you have two parallel plates evacuated between them.
That's right.
And there's a point where they actually feel a whole other force attracting them.
And so what that force really is in the region between them, the vacuum fluctuations are suppressed. And so you have negative energy in between. That negative energy is sucking them together. And they can do work on you if you're holding on to these plates, and they attract each other.
You have to put energy to resist it.
You put energy in as they go together. They do work on you. The electromagnetic field between two plates in the Casimir effect is exotic.
Okay.
And so
you have this in your basement, is what you're telling me.
Yeah. Well, I don't have it in my basement, but physicists do this. Let me just say as a side remark, having learned a lot about vacuum fluctuations, we in LIGO and our gravity wave project.
Oh, I want to get to that.
But I'll just make the remark that the LIGO team has perfected a technique called quantum precision measurement, which is based on manipulating vacuum fluctuations in order to circumvent the uncertainty principle. And so this business of manipulating vacuum fluctuations is something we do in modern physics. And it is something then that you can imagine, you can ask, can a very advanced civilization manipulate vacuum fluctuations adequately in order to make enough exotic matter inside a wormhole to hold the wormhole open? And so I posed this as a question to my physicist colleagues, stimulated by Carl Sagan and him wanting to send his heroin through a black hole. I said, no, use a wormhole. And so we got to hold it open. And so physicist colleagues, please help Carl and figure out, can an advanced civilization do this? And the answer is we still don't know. 40 years later now, we still don't know.
Right. Well, we're doing magic compared to what anyone thought was possible 50 years ago. Certainly at the dawn of quantum physics, we're on the centennial of the decade of quantum discovery back in the 1920s.
Right. Well, I was very close friends with Carl Sagan, and I've developed close friendship with Christopher Nolan. Chris has a very different background than me. He knows a lot of science, but he's learned it all by browsing the web. And he knows it well enough to ask me hard questions. That's just like you do. But he asked them first, so I have the answers now. So he has inspired me to ask questions that then I sort of translate to and give to colleagues, because my colleagues are smarter than I am. My role is to pass on interesting questions.
You're the conduit for this.
Conduit for interesting questions for my colleagues to work on.
So, dude, you can't leave well enough alone. Einstein says maybe there are gravitational waves emanating from major gravitational disturbances in the universe, and you got to go up and find them. But you're not the first to have attempted this, right? At the University of Maryland, there was Weber, I think. What's his first name?
Joe.
Joe Weber,
Joseph
of course,
Weber.
Who had a cylinder, if I remember correctly, where he was trying to measure whether if a gravitational wave washed over it, he could detect a distortion in the shape of the cylinder, I think was the goal.
Yeah, well, the gravitational wave would drive vibrations of the cylinder. End-to-end vibrations.
Okay.
And so he instrumented it to search for changes in the amplitude and phase of vibrations of the cylinder. The cylinder is at a finite temperature, so it's always vibrating a little bit because it's a finite temperature. And so he instrumented it with what's called piezoelectric transducers that he glued around the middle of the cylinder, that when they were squeezed, they would generate an electrical voltage that he could measure. And they're amazing things. This piezoelectric transducer is just absolutely amazing. You squeeze them a tiny, tiny bit, and you get a big voltage out. And I mean, Joe Weber was tremendously creative. He was,
I think he was working on that while I was at the University of Maryland. I was there in the 80s. Yeah. I think he was still working on it.
Yeah, that's right. So he began working on it in the late 60s, early 70s, and announced that he was seeing possible evidence for gravitational waves. There
was a lot of skepticism at the time, if I remember.
Right. I'm sorry. He started working on it in the late 50s, early 60s, announced in 69 that he was seeing some possible evidence of gravitational waves. And a number of other physicists around the world built similar detectors. And the bottom line in the end, after a period of shaking out, was that others were not seeing gravitational waves.
And that's the only way science works. One person's result is not a result until somebody else, a competitor, somebody else who uses different wall current, somebody from another country. You need multiple verifications.
But on the other hand, Weber, Joe, he started the field. He triggered this work. The approach that he invented for searching for gravitational waves was the dominant approach from then until the 2000s. And a number of other research groups built similar detectors and improved them better and better and better over that period of time.
On that model.
The model. So I mean, I have enormous respect for what he did.
Sure. Now you decided to, you and others decided to look differently for them.
Yeah. Well, so Ray Weiss, Rainer Weiss, Ray, his friends call him, at MIT was the primary inventor of an alternative technique that was the technique that ultimately succeeded. He invented it. He wrote a technical paper about the technique that identified all of the kinds of noise that you would have to deal with, and it explained how you might deal with them, and did analysis of how good this detector could be. And he put it all in this
there's the recipe.
paper. So
my gosh.
It was a recipe for how to go forward. And he wrote this in 1972. And Ray, being Ray, didn't publish this because I think he figured you don't publish until you have built one and seen a gravitational wave.
Mm-hmm.
So, but however, Ray sent copies of this around to all his colleagues. And he put it into quarterly reports of the MIT laboratory in which he worked. And so it is probably the most influential non-published paper, certainly that I know of in physics. I mean, it was a tour de force, and it triggered the huge effort.
The next generation
that actually succeeded.
I was fortunate enough to visit because there were two LIGO experiments, one in Louisiana and the other one is in
Hanford, Washington.
Hanford, Washington. Why do you have two? Because you can't just have one result.
Yeah, you're looking for an effect that is so small that you wouldn't believe it unless you see it on two independent instruments.
There you go. So you've got these pathways. Are they a kilometer long?
4 kilometers.
4 kilometers long. Evacuated. You send a beam of light that is split from a laser that's split. It goes these are at 90-degree angles, and they go to the end. They get reflected back, and you rejoin them, and you want to see if their waves line up. And if they line up, then each direction is identical. You can go home. If they're slightly different, then one of these legs experienced a different encounter with the fabric of the space-time continuum than the other did. That's audacious.
So actually what you want to do is you make them slightly different in the first place, but then, so that means you send your laser light in from this direction. There's a beam splitter where the light gets split in two to go down the two arms. So the laser light goes in like that. There's this beam splitter, so the light gets split in two into one arm in that direction, the other arm in this direction. And then it comes back and recombines in the beam splitter. The laser light was coming in from this direction, but when it recombines, a little bit of light goes out in a perpendicular direction. So you have a laser here and you have an output over there. And the output direction is the direction that has a signal. And if the length of one arm is shortened and the length of the other arm is lengthened.
And that would only happen because a gravitational wave washed over that arm.
That's right. Mm-hmm. Then you get a change in how much light is coming out to the output.
All right. So you're trying to find a length difference. And if I remember the materials from the press releases, that is equivalent to 1/10 the diameter of a proton?
No, it's equivalent to, it's 10 million times smaller than an atom and 100 times smaller than a proton.
1/100th the diameter of a proton. Meanwhile, all the world is vibrating because everything is at a temperature. And cool it as much as you want, there's still vibrations. And somebody is walking down the street. I remember being on campus there. Can I call it a campus? That's what it was. And you can detect cars on the road a mile away. You have to insulate this. That's half the science done for the experiment. You should get a Nobel Prize for that.
Well, that's what the Nobel Prize was given for. For that, yeah.
To have successfully isolated the effect you're trying to measure.
So the way I like to describe it is you're bouncing light off of these mirrors, and you're looking for a motion of the mirrors that is 10 million times smaller than the atoms of which the mirrors are made. And the mirrors, the atoms in the mirrors themselves are vibrating because they're at finite temperature by an amount that is about the same as their size. So 10 million times smaller than the atoms, and 10 million times smaller than the vibrations the atoms are undergoing.
So once again, in physics, there's a phenomenon we're trying to measure, but it's kind of buried, and you need a way to get to it. And it seems like half, if not more than half of the effort is how brilliant is your engineer that you've brought onto the task to accomplish this. How good are your tools? It's not just the idea. It's now you got to make the damn measurement. And it's not obvious. You need very talented people assembled for this.
Absolutely. And so that was the issue, is how good a team can you put together? So when I learned of Ray Weiss's idea, and I knew roughly how strong the strongest gravitational waves would be, I knew already then that it would be necessary to...
This would be the collision of two black holes.
Collision of two black holes.
And you can't just summon that up. There has to be real things in the universe that might produce that.
That's right.
You can't just wish for it.
But based on what we knew about the universe at the time, I was estimating a wave strength that was roughly correct. And it was at that level that you would have to monitor the motion of these mirrors at 10 million times smaller than the atoms in the mirrors. And I thought to myself, that's crazy. And so in this book, which was published in 1973, we went to press just after Ray Weiss wrote his seminal paper. I had not yet really studied that paper fully, but I just knew that this was crazy. And so it describes in a few words Ray's idea in here. And then it says, I think there's an exercise where it says, show why this is not very promising. Just a mild, gentle.
Because it is a textbook, right? You get to declare
so there's
that.
the students challenge to show why.
Well, it could not be a very good idea in 1973, but fast forward a half a century,
right? And so, so it is
1853. Flying is not a good idea. Write an essay on why flying isn't a good idea.
Yeah, but that was the central issue. If we worked for a few decades, did we have a shot at success? In 1973, I thought, no way. But by 1975, I had turned around. I'd had long conversations with Ray. I'd had long conversations with Vladimir Braginsky, a colleague in Moscow. I'd done lots of calculations of my own. And I came to the conclusion that you had a real shot at success if you put together a superbly strong team and you worked at it for a few decades.
And you need money, and you were well supported, I think, by the National Science Foundation.
Well, not yet. So at that point, NSF had given Ray $60,000 to get started. And
$60,000.
That's how much he had in the 1970s from the National Science Foundation. He also had some money from the Air Force Office of Scientific Research. I'm not sure how much he had, or he'd had that until in the Vietnam era they stopped supporting science. due to something called the Mansfield Amendment, American politics. And that's when NSF picked him up and gave him $60,000. That was a drop in the bucket compared to what was needed. And NSF wasn't about ready to put big money in.
This required some members of your team to like appear in front of Congress to defend this.
That's correct. And
Okay.
But that was much later. The issue was getting started. And so how did we get started? Caltech is a very different kind of an institution than any other I've ever dealt with. At Caltech, I was able to propose to my colleagues that we get into this field, that we build a experimental program in parallel with Ray Weiss's program at MIT. So the chair of the Division of Physics, Mathematics, and Astronomy at Caltech set up a committee to look at it. Committee looked at it for about 6 months, detailed study, came back and enthusiastic, said, let's go ahead. And so Caltech put private money, about $2 million of its own private money to get started. And that inflates to about $12 million today of private money when nobody else is putting anything in.
No, you're right. That's a very different, a very different culture at Caltech, as you described.
And once that had happened, and we had brought Ron Drever from Scotland to start the experimental effort, then NSF stood up and took notice. They did their own study of this and came up with the same conclusion. And they started funding us and Ray Weiss, and it became a Caltech-MIT collaboration.
Let's fast forward to 2016, where you make the first detection.
We announced it in 16.
You announced it in 16. By the way, I would later learn that when I visited the facility in Louisiana, you already had made the detection. And you'd be happy to know that everyone was completely zip-mouthed about it until it was officially. Because I have this huge internet following, right? And people were totally zip-mouthed. I swear I didn't know about it until the press release came.
Yeah, we were all sworn to secrecy.
Yes. And so the confirmation of a first detection came from the second facility built in Hanford. And at that point, you have a time delay because gravitational waves move at the speed of light, correct? So, and Earth is a finite size. And so all that worked out.
Yeah. And so it was just 7 milliseconds, 7/1000 of a second time difference, because the waves came up from the south. They entered the Earth around the tip of the Antarctic Peninsula, traveled through the Earth, came up through the Earth in Louisiana first, and in Washington State second, 7 milliseconds later. And then the waves were unaffected by all the matter of the Earth. They couldn't see the difference between Earth and no Earth. And they couldn't see the difference between detector and no detector. They were very hard to detect.
They're doing their thing. So what impresses me greatly is here we have a prediction made by Albert Einstein when in 1916 or 15, whatever. Albert Einstein, in a little known fact, I mean, physicists know this, but I don't think the public knows, Einstein laid out the equations for the stimulated emission of radiation, which is the physical foundation of a laser.
Yeah.
He wrote that down first.
Yep.
And a laser would take a few decades to actually be built into the 1950s. And I'm just saying, here's Einstein predicting gravitational waves, laying the foundation for a laser, and 100 years later, his gravitational waves are found with lasers.
Yes.
So these are crumbs spilling off his plate.
Einstein was kind of smart.
And lo and behold, nobody's surprised, the Nobel Prize goes to this project. And you, along with Ray Weiss and Barry Barish, share the Nobel Prize. What year was that? 2017.
Yeah. So they apologized to us that they didn't give us in 16 because we didn't announce it until past their deadline for
well, plus
nominations.
they delay anyway. They never.
They said it obviously. It was obvious the prize was going for this. It was just obvious.
Yeah. Hey, StarTalk fans, I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. You can't be a general relativity Einstein guy without being a black hole guy. So forgive me for asking you to retell a story you've probably told 1,000 times, but there's some famous bet you made. Was it with Preskell, with some other physicist?
Preskell and Hawking.
And Stephen Hawking. By the way, I was at the University of Texas when Preskell was there. I think he was like a postdoc or something. He was just starting out. That's how old I am. I'm an old guy. I'm an old guy.
You're a young kid.
I'm an old man.
You're a young kid.
So you made a bet, and let me see if I can set the table here. A black hole, once we all agree that they exist, we can ask other questions. When you have something outside the black hole and it falls in, what happens to that information that was contained in that object? Is it gone forever, and is that okay? Because information theory was a whole branch of science, shall I call it science, that was rising up at around the same time, and entropy became a buzzword among many. So what was the bet, and how was it ultimately resolved?
So the bet was between Stephen Hawking and me on one side, and John Preskell on the other side. And it was over whether or not information does get lost in black holes. The background of
why is that so bad?
Okay, so it's bad because the fundamental laws of quantum mechanics, as they are normally formulated, physicists are widely agreed that quantum physics is fundamental and that quantum physics underlies all of physics.
It's the most successful theory ever put forth of the universe.
And classical physics, where there are not these quantum fluctuations, there are not these probabilities, that arises from quantum physics as an approximation under ordinary everyday circumstances.
There are many people who caricature science, physics in particular, by saying, well, we used to think classical physics was it, but now we discard it in favor of quantum physics. But that's not true. No, quantum physics absorbed, as well as relativity, general relativity, absorbing Newtonian gravity.
Yeah,
it's not discarded. It's a bigger understanding, a deeper understanding.
Right.
Okay. Just want to emphasize that.
That's right.
Many people get that confused.
And so quantum physics is normally formulated is almost universally viewed, has built right into it from the very beginning the fact that information cannot be lost. Now, these words, information cannot be lost, are a translation into everyday language of something else, which is not everyday language, which says that the evolution of everything in the universe is unitary. And so those are buzzwords that are not part of the normal lexicon. But I want to say that to indicate that there's some very, very extremely precise version of this, of which information is being lost, is a colloquial way of saying it.
Okay. But it would represent a violation of some fundamental tenets of quantum theory.
That's right. Stephen Hawking, back when he was visiting Caltech,
who, by the way, we've interviewed for StarTalk in our archives. Check it out.
In 1974, 75, he spent a year in my research group at Caltech. We were very close friends. And during that period, he having discovered something called Hawking radiation, which is a very slow evaporation of a black hole. It emits radiation and slowly evaporates. He then, while he was here, began to look much more deeply at quantum theory and black holes. And he came up with a prediction that information really is lost. And when black holes evaporate, you could form a black hole, if you waited long enough, much longer than the age of the universe for normal black holes, the black hole would evaporate and all the information that went into the black hole would be gone. The black hole would be gone. You just simply lost the information. It no longer is there. And that was complete violation of the normal tenets of quantum mechanics. And yet he was claiming that that was true. He wrote a paper on this with all the technical details. He couldn't get it published because it was so obvious. It had to be wrong, but nobody could see anything wrong in his calculation. And so he had to fight for more than a year to get it published. If you look at this paper, you see the submission date.
As all research papers give you. Yes.
Yeah, they give you a submission date, and then you usually have a revised date, and then it's published. There's no revised date. There's a submission date, and the publication date is something like nearly a year and a half later. He fought for a whole year, more than a year, to get this thing published. And physicists struggled with this ever since. So those of us whose roots are in relativity tended to believe Hawking. And those of us whose roots who grew up with quantum mechanics instead of relativity first, those of us who were enamored of relativity tended to believe Hawking. And so Hawking and I made this bet with Preskel, whose roots were in quantum physics.
And he's the junior of you both, right?
He's the junior
young
of us
whippersnapper
both.
coming up.
He is now the Richard P. Feynman Professor of Theoretical Physics at Caltech. I'm the Richard P. Feynman Professor of Theoretical Physics Emeritus.
Emeritus. Okay, them young whippersnappers. Oh, man, they'll take your job in a minute.
I turned the chair over to John. I mean, John is brilliant. He's a hell of a lot smarter than I am. A hell of a lot smarter. Anyway, so we made this bet. And this was in a period when Hawking was starting to visit Caltech for typically 3 to 6 weeks every year.
Was he yet wheelchair bound?
Oh yeah, he was wheelchair bound, going way back to about 1970.
Okay.
And this is 1990.
Oh, much
So
later.
this is-
Okay.
We made the bet around 1990.
So the stage is set. Okay, the cage match is set. You and Stephen Hawking, titans in your field, in your subject, conclude, yeah, information is lost. Especially if Hawking radiation, you can evaporate the black hole and everything is gone. There's no memory of what was there. Preskel is declaring that information is not lost, and his roots are deep in quantum physics, which we know has never been shown to be wrong.
And they're both smarter than I am. And they both know a lot more about quantum physics than I do, because we'll return to this. But let me just explain that through my whole career, I've thought that the quantum gravity, combining general relativity with quantum physics, was the most important area of physics of all. But I also made a decision when I was very young, I will never work in quantum gravity because the field is too crowded. There are too many smart people there. I will pick, I'm smart enough to pick really important problems that I can solve that nobody else is working on. and they'll only figure out later that I'm right, that those problems are important. But I won't touch a problem where everybody's
we got 1 million
working.
people in the room.
Just too many smart people.
Too many smart people in the room.
So anyway, so they have now agreed that information is not lost.
So Hawking conceded, and by association with you, or are you still a holdout on this?
No, I'm still a holdout.
Okay. And what led to this concession, if I understand correctly?
So Stephen, together with a student, was working on a idea for how the information might be recovered. And he basically said that in quantum physics, if you form a black hole and then it evaporates, there's also a tiny probability the black hole never formed in the first place, and the information sneaks out through the root where it didn't form in the first place. And
I'm sorry, that sounds like a cop-out.
yeah, it does sound like a cop-out, but it's very clever, and it's in keeping with how physics works. but it's not obvious that it's right. But it's conceivable that this is
What about
happened.
the idea? So maybe I've misunderstood. So I got to go back to see where I've said this even publicly. I thought as the black hole evaporates, because the energy, the gravitational energy in the vicinity of a black hole can spontaneously make a pair of particles. And one particle escapes, the other one falls into the black hole. And this just keeps going until there's no black hole left. But the particle that escapes, if you inventory those particles, they're real particles. And don't you recover all the particles that went in the first place?
Well, you recover all the energy.
But
they don't recover
not the inventory of particles, the quarks.
You don't get the same particles necessarily.
Okay, then I misunderstood that. I've been wrong. I think I've been wrong. I thought you get particle for particle, they come out, which blew my mind.
I don't think there's no proof that that's the case.
Well, of course, we
certainly no proof that that's the case. I don't think it is the case.
Okay.
But
so you guys lost the bet.
Well, no.
Okay. Hawking concedes the bet.
Hawking concedes the bet.
And what was at stake for this?
The loser will give the winner an encyclopedia filled with information that that somehow escaped the black hole, and so. So
information is the penalty gift.
That's right. So Stephen Hawking conceded the bet at a big international conference on general relativity and gravitation in Dublin, Ireland, in early 2000.
Were there gasps in the audience?
There were rumors that he was going to concede. And so there was a big ceremony. I played some role in the ceremony, but I didn't concede myself. So Stephen gave Preskill, who's a big baseball fan, an encyclopedia of American baseball.
Any kind of encyclopedia.
Yeah.
Okay.
Well, that was his idea of.
That's clever.
So anyway,
and less expensive.
Yeah. I didn't concede for a peculiar reason that there is an alternative formulation of quantum mechanics in which information could be lost. It's due to Feynman, called a sum over histories formulation. And as I say, I don't work in quantum theory in any deep sort of way. I do in terms of quantum technology, which we needed for LIGO, but that's a separate story. But two of the very deepest physicists in working in quantum theory of my lifetime were Murray Gell-Mann and Jim Hartle. Jim Hartle at Santa Barbara, Gell-Mann at Caltech, and then he moved to the Santa Fe Institute in retirement.
Gell-Mann is credited with proposing quarks as the fundamental particle of...
The giants of theoretical physics when I was a young physicist at Caltech were Gell-Mann and Feynman. And two colleagues of mine that I enormously respect. So Gell-Mann and Hartle took Feynman's path integral or sum over histories approach to quantum mechanics, and they developed it further in a form that they could apply it to cosmology, to the universe. And then Hartle has used that to study quantum cosmology, the quantum mechanical description of how the birth of the universe and how it has evolved. That particular approach to quantum mechanics, Hartle took it and he showed how that approach can deal perfectly well with information loss. And it deals with it. It arises because of what we call closed time-like curves. There's a certain probability for backward time travel in quantum physics. In this Feynman, Gell-Mann, Hartle approach, there's a certain probability for backward time travel. And if you can have backward time travel at the quantum level, then you lose information. And there's an elegant mathematical formulation here.
Quantum physics is so weaselly this way.
Well, that's not the standard version of quantum mechanics, but that was the version that Feynman and that Hartland-Gell-Mann needed in order to do the quantum mechanics of the entire universe and the birth of the universe. So that we're getting into this issue of the birth of the universe and quantum gravity here, and I am rather enamored of this approach. Although I don't do it, I just look on the sidelines and admire these people who are smarter than I am and who have the courage to work in a crowded field. But I'm just so impressed with this, and with the fact that within that formulation, you can lose information.
Is that the start of a formulation that will one day marry general relativity and quantum physics?
It does do that. It's not. It's
knocking on the door.
It's knocking on the door.
And so remind me now. You're Professor Thorne in this question. What is the problem with general relativity not melding together with quantum physics? What is the real holdup there?
Well, the real holdup is that they are logically incompatible with each other, and so something has to give.
And that's because of the general relativity requires space to be a continuous.
You have a continuum space. And it's a very definite space. It's not a space where you have a certain probability that space is warped in this way and another probability is warped in that way.
In fact, there are no probabilities at all.
Yeah, there are classical probabilities, but not
quantum.
Probabilities.
And so at the smallest scale, they're incompatible.
The smallest scale, they're incompatible in any place where gravity becomes extremely strong. They're incompatible. So the smallest scale, they're incompatible. Even here in this room, but also they're incompatible. They're incompatible in the birth of the universe when gravity was extremely strong. They're incompatible in the core of a black hole where gravity is extremely strong. They're incompatible if you try to make a time machine. Hockey and I, independently with our students, sort of identified a process whereby if a very advanced civilization tries to make a time machine, it will quite possibly explode at the moment you try to turn it on. And that's also controlled by these laws of quantum gravity.
So that's why we haven't seen any time travelers yet.
Well, that may be the
reason. It would
reason.
explain it. They're all dead trying to turn on the machine.
That's right.
What you're saying is Einstein puts forth the general theory of relativity, which is so successful in so many realms, and it picked up where Newtonian gravity failed, yet we must confess or concede that there's a limit to how far general relativity goes, although we've yet to find a limit to quantum physics. So the betting pool will say general relativity is going to succumb to quantum physics in some way.
Yeah, that's one way to say it. Certainly there is this incompatibility between the two.
And string theorists are trying to be they're like performing the shotgun wedding between the two branches of physics somehow.
Yeah, and I do think, again, looking in from the outside, since I've chosen not to work in this field, that string theory is likely to be a successful route into the correct laws of quantum gravity. Yeah, but they've
been at it for 50 years.
Oh, yeah.
40 years.
Not very long. Come on, I'm 84 years old. Come on. That's just a drop in the bucket. Come on.
Wait, but Einstein went from special relativity to general relativity in 10 years. Kepler went from weird nested solids to the Kepler's 3 laws of motion in 10 years. And that's lone scientists.
We've been working to try to do controlled fusion for
50 years.
More than 50 years.
Yeah.
LIGO took 50 years from the time I first started working on gravitational waves until we succeeded. It was 50 years.
Okay.
Some things take a long time.
Yeah, but LIGO is a machine. The merging of quantum physics and general relativity are ideas. Could it be? And I've said this, I don't want to say this to you because you're Kip Thorne, but I've said this to Brian Greene, okay? Because Brian Greene's like my generation. I said to Brian Greene, I said, Brian, you've been working on string theory for decades. Maybe all of you are just too stupid to figure it out and we're waiting for someone else to be born into this field to then solve it in the ways none of the rest of you can. None of them are saying, I'm too stupid to figure this out. Let me choose another profession. No, they're saying the problem is too hard. And if you go 40 years of really smart people not figuring something out, that tells me either they're barking up the wrong tree or none of them are smart enough. Mm-hmm. Am I overreacting here?
I think you have to remember that we do build on each other.
Yeah.
And none of them by themselves are smart enough.
Okay.
But the community, again, it's like this Nobel Prize really belongs to 1,000 people. It doesn't belong to me.
Mm-hmm.
With
a genesis in Joe Weber.
With a genesis in Joe Weber, we build. Newton spoke of standing on the shoulders of giants, and that really is true.
If I can see farther than others, it's because I've stood on the shoulders of giants who have come before me.
And that's the nature of science. And the struggles that our colleagues have been having with string theory and M theory and quantum gravity, we've learned an enormous amount. It shows it's very promising, but it's going to continue on into the next generation before the ultimate success is had, very, very, very probably.
Those are like final words right there. Those are like... Kip, I've heard rumor that whichever faculty of Caltech gets a Nobel Prize, they get a parking spot with their name on it. Is that true?
When at Caltech, a Nobel Prize does not get you a parking spot with your name on it. You have to pay for the parking spot just as much as you do without a Nobel Prize.
Okay, but that was such a fun rumor, though. I heard
That's true at USC, but it's not true at Caltech.
Okay, because there's just too many of you all running around with Nobel Prizes. Then the parking spots are too valuable. So true at USC. Okay,
yeah, it is true at USC.
All right.
Yeah.
So you're 84. You have 84 years of wisdom coursing in your veins and arteries. Are there any projects you're working on in the next several years?
So I made a gradual transition, conscious, away from science, away from scientific research, beginning around 15 years ago.
Oh.
I would like to believe I can live to 110. That's my intended goal. And so for the next remaining decades, I wanted to do things that I really enjoyed. And I've enjoyed science. I've been a conventional Caltech professor for half a century. Enormously enjoyed it. Enormously enjoyed working with students. I trained over 50 PhD students and who did far more important research than I did. And been there, done that. And I have worked in all these areas of science, and I've had enormous fun, but I've turned them over to the younger generation, and they're smarter than I am.
Okay, so what are you surfing now or skydiving? Okay, you're taking up other...
So I decided that I would like to spend a few decades doing creative work at the interface between science and the arts.
Oh.
So Interstellar is an example.
That was going to be released in September, and then they delayed it to the holiday season in December.
So the re-release of Interstellar.
The re-release to December 2024.
That's
okay.
right. That's right. That was enormously enjoyable. I learned how great it can be to collaborate with somebody as brilliant and as completely different than I am, Christopher Nolan. So my most recent collaboration has been a book of poetry and paintings with Leah Halloran and about the warp side of the universe. And my poetry, my attempts at poetry and her paintings, but just trying to see whether it's possible by tightly integrating paintings with verse to convey the essence of issues in science, the spirit, the essential features without conveying the precise details. No, that's not the right genre for precise details. But anyway, so I've been enjoying that.
By the way, I've always felt that way about Van Gogh's Starry Night.
Yes.
where you look at that painting and you say, this is clearly not what he saw, but it's definitely what he felt.
Yes. Yes.
And you get
Yes.
to experience the universe through his own lens.
Yes.
And so I've always appreciated art when it plays that role.
Yeah. I have a second movie that's been in the works for more than a decade.
Ooh, can you tell? Can you?
Well,
can you?
it's just something that I started with Stephen Hawking and Linda Opst, who was my partner on starting Interstellar, and is wonderful to work with. But that movie might never get made. I'm not going to tell you what it's about, aside from the fact that it's sci-fi, and it's solid sci-fi. So it's science built in from the outset. So if that does not work out in the end, then I may try turning it into a novel. I've never tried to write a novel. I don't know whether I can, but it would be fun to try. And actually, the thing that I have put almost a large fraction of my effort in, the lion's share of my effort in since the beginning of the pandemic, is a history of the LIGO project, the LIGO Gravitational Wave Project, because that is, I think, pretty clearly the technically most difficult thing that's ever been done by physicists.
By anybody. By anybody.
Yeah, probably by anybody. And
1/100th the diameter of a proton, that's anybody.
And success required both developing amazing technology, new technologies. It required developing computer simulations of colliding black holes, required developing quantum precision measurement technology that is now in LIGO and is playing a major role, where you circumvent what's called the Heisenberg uncertainty principle.
My mind is still partly blown by you having said that. You're bypassing Heisenberg's uncertainty principle.
That's right. By manipulating vacuum fluctuations, just like advanced civilizations
might do as a routine thing.
Yeah. So we developed this new area of technology for LIGO. But it was also a very political thing. How do you get $1 billion of taxpayer money for a field that didn't exist when you began?
And should they bet on you and not someone else?
That's right.
And plus, I think you even had naysayers, if I remember correctly.
Yeah, yes.
Colleagues would say, "This is a pipe dream."
We had political battles in Washington.
Yeah. Tell me who the naysayers were. I got people who could take care of them.
They were some of the leading astronomers.
I got people take. You want my people to?
No, they've come around.
You think? Okay.
they've come around because this is so exciting now that LIGO succeeded. But the sociology of the transition from small science to big science is a very rocky process.
And that's the right word, sociology, because that's what it is.
I don't like working in a big science project. It's not for me. Just like working in a crowded field is not for me. But we had to this had to make the
It wouldn't have happened otherwise.
Transformation wouldn't have happened otherwise. And the genius of Barry Barish in making that happen was, and the genius of Robbie Vogt in getting us partway there at the very beginning is our initial director, who was the one that sold it to Congress and it really got us going. It's a very complicated story, and I have a set of 5 collaborators that I've been working on with this history. We just finished draft 6 and sent it out to LIGO colleagues to comment on. And I have getting back huge numbers of comments, and it'll take me 2 more years, I think. So anyway, this history, because of the nature of this project, it's a very interesting and complex history that is quite important for the history of science.
Especially when you consider most people knew nothing of LIGO until they see the headline that it discovered gravitational waves. Right. And why would they have any thought of what challenges preceded that? You know, they just read the result. Oh, scientists discover this. Well, how about the like you said, the politics, the sociology, the genesis, the who's standing on whose shoulders, who are the naysayers. All that has to be overcome.
The international collaboration, key input from the Soviet Union in the depths of the Cold War. And I mean, it's just a fascinating story. And enormous fun.
You know what Arthur C. Clarke said? He said, in space where there is no air, a flag will not wave. So maybe the universe is not a place where we should be waving flags. Collaboration is what gets you there.
I like that.
So, Kip, this has been a delight. Thanks for making time.
A lot of fun.
For StarTalk. I look forward to the re-release of Interstellar. We're recording this before that has come out. And you already know this, but let me reaffirm that that film just took people on a ride far beyond anything they had imagined. It had a kind of an impact on people in the way 2001: A Space Odyssey did. It was mysterious, it was modern, it was the future, but it was still relevant. But it left you with more questions to ask than questions answered, and that you want that, I think.
Yeah, and that was really the genius of Christopher Nolan, taking some science that he and I had put together, but combining it with a human story that was powerful, and
with marquee director and marquee actors that made sure it would get noticed.
And music.
Yes.
I went to a concert by Hans Zimmer. Who
that was Hans Zimmer, yes.
Just, I think, the night before last. And he let loose what I didn't know there, that he basically said that the music, certain pieces of the music in Interstellar were as close to perfection as he has achieved.
Wow. I'm going to give it another listen, because there is no 2001 without its musical track, with the Strauss waltzes,
but this is very different. I mean, it's all Zimmer's original music, and it's a remarkable score. Just amazing.
I look forward to your next 25 years when you live to 110. Maybe we can do a reprise of this conversation.
Yes,
we'll check in on you.
On that.
See how you've been coming along, dude.
Okay, thanks a lot.
Thanks.
Great to see you again.
Thanks. This has been a special conversation, exclusive one-on-one between StarTalk and Kip Thorne, Nobel Laureate. Even let me touch his medal. First time I've ever touched a Nobel Prize.
Well, the medal that really belongs to 1,000.
The medal earned by a huge team, as he humbly declares. And as we enter a new era of science, where collaborations are really how this works, especially where you have international collaborations, you have scientists getting along, even at times when the leaders of their countries are in conflict. That's just messed up. That's messed up. I'm Neil deGrasse Tyson, your personal astrophysicist for StarTalk. As always, I bid you to keep looking up.
Thank you.